Right, let's have a look. Last topic. What are you guys laughing at? Huh? She likes who?
She liked him.
Who'd she like?
Lied. She lied to me.
She lied to you?
As always.
What did she lie about?
What?
What did she lie to you about? Nothing. Okay, nothing important. Right, am I recording? Quantum mechanics. Yeah? You got that? So, have you ever heard of this before? No? Where have you heard of it before? If you've heard of it?
Entertainment.
Yeah. Sci-fi.
Yeah.
Yeah, where else?
Oh.
You heard of this?
Yeah, we have some word in Chinese. This one.
Really?
This is like a subject.
Yeah, it is. Yeah, correct. Yeah. So, I don't know if we can. Sorry. There's a lot to do, so we might only get half of it done, but we can do our best. There's a lot to do. Okay, so Earth and Moon. Now you don't need to write this down. This is just to get us thinking. What type of motion is this? It's circular. Now, when you look at this formula, you have a constant, mass, radius. And you can move in a circle. And you can move in any orbit, right? For example, could you have a satellite here? You could have a satellite here. Could you have a spaceship here? You could have a spaceship here. Could you have the moon here? You could have the moon here. You know, like you can be going in any orbit, right? Now, let's have a look at this. This is the hydrogen atom. It's a proton, electron, and look at the formula. F equals K, Q1, Q2 over R squared. So we think, okay, this is similar to what we had in the last picture. So the electron could be here, so maybe the electron could be here. But you know from chemistry that there's only certain orbits your electron can be in, right? You know, you've done these orbitals in chemistry, yeah? And why is that? Why can't the electron be here? Were you told this? Or were you just told the electron could be in orbit 1, whatever it is? What's the first one? S1, isn't it? Yeah. And the next one? Yeah. But were you told why it can't be in between? Just a mystery. It's either here or it's here. So, the reason is, I lied when I told you something in the last class. So, what was the lie I told you in the last class? The lie was, I said the distance could be smaller, and I said no smallest distance. This is not true. There actually is a smallest distance, and if you have less than this smallest distance, you have no distance. This is true. So the reason, one of the reasons that the electron can be at certain levels only is because it can only be at certain distances. Because there is no smallest distance. It can only be in certain places. Because if it's here and if it's here, and this is the smallest distance, then it can't be in the middle, because that would be half the smallest distance. You can't have. Now, is there anything I need you to write yet? No, it's okay. But I will need you to write this down in a moment. I don't know if you've done this in chemistry. You've done something similar to it. Well, maybe, I don't know. What do you call it? You have your ionization chamber. So you put in the gas and you heat it up, and then you fire it and it goes through the accelerator and so on. There's something simpler here that you could do. I'll try and just draw a picture for you. So, the first one is The first one is if you just had perfect white light, you know, from something like the sun, for example. If you put that light through a prism, you probably saw this in middle school. If you have your prism and you shine your light through it, then what do you get here? You get all the colours. So you get a picture like this. You learned this, I think, in middle school, right? Did you remember who did this experiment? Newton, yeah, he was the one who did this experiment. Okay. Now, instead of having sunlight, suppose you did this. Suppose you had some hot gas. And so the hot gas is glowing. So there's some light coming off the hot gas. So this hits the prism and it also makes a picture. However, the picture is not like the first one. What is different about this picture? There's lots of colours that are missing. You have some colours, but you have lots which you are missing. And then the last one is when you have a cold gas. So you have a cold gas, and here you have some light. So what you do is you shine the light into the gas. It comes out of the gas, hits into the prism, and again, it makes a picture. Now what's different about this picture? It's kind of the opposite to this one, isn't it? You have lots of colours, but there's a couple of colours that are missing. Now the question is, why does this happen? Well, let me explain why. So here's our gas, here's our atom, here's our electron. Okay. Now, let's see. We'll do this one here's the easiest one first. So we have some light that comes in. This guy is trapped. So what is its potential energy? Its potential energy is negative if it's trapped. Okay. Now, if this light has enough energy, it will free it. But then what happens to the light? It disappears because it was used to free the electron, to ionize the electron. Suppose that it has less energy and it hits the electron. Will it free it? No. So it just continues on. So you can see that if you have the right frequency, then it will free the electron. But the light disappears. So what happens is, the reason that there's some colours missing here is because those frequencies were taken by the electron and used to free the electron. So the light disappeared then. You got the idea? Yeah. So then what's happening here? Well, this is something similar. It's just the opposite. So remember we said we can use a photon to free an electron. So it's the opposite picture here. The electron can be used to release a photon. So instead, you have a picture like this. You have the atom, and you have no electrons, for example, and then an electron comes along and then gets stuck in an orbit. So then what happens is the photon is released. So it's just the opposite picture to what we did a moment ago. So instead of all these missing colours is because it'd be easier to say, all these colours here are caused by the photons being released when the electron became trapped. Okay, so the electron became trapped and released a photon. So it's the opposite picture here because the situation is opposite. Here, electrons are flying around because it's hot, and you know when it's hot, there's lots of kinetic energy. It releases photons. Here's the opposite. The gas is cold, so there's not really kinetic energy, and the photon comes in and frees an electron. Yeah? So this is called the emission spectrum because it represents the photons that were released. And this is called the absorption spectrum because it represents the photons that were captured. Now what's really interesting about this is that this picture is unique for every material. Every material. It's like a fingerprint. Each different material here will produce a different image. So for example, if I was to say take this plastic and I was to heat it up and make it a gas and then shine a light into the gas, I would get a different image there than if I took, I don't know, like this cloth here and turned it into a gas. So this is how you can identify what a material is in chemistry. In chemistry, if you had some material and you don't know what it is, you can take a small amount of it, you can heat it up into a small gas, you can shine a light into it, you can make this image, you can put this image into a computer, it can search a database and find the material. So this is how people can tell what a material is, using this, it's called spectral analysis. Have you heard of this in chemistry, or is not come up in chemistry? Spectral analysis? No, okay. If you do chemistry at university, you come up with it. So what I need you to do is to do your very best to try and draw these. Yeah. Can try to draw. Got that? You got it, Siba? Who am I waiting for? Andak and Chow, okay. The three of us will just rest for a minute. quantum, poor Kim. Here, I have water here if you want to spray you.
That's fine.
Are you sure? Siva will clean it off for you, won't you, Siva?
Could you hold like a bad hair and cancer? No? No, so I moved. That's bad science.
Yes, bad science, good.
Julie's.
How did you do in your active listening? Did you get your grade back? You didn't get your grade back yet?
We never get a grade spot.
No, I thought you got your grade back for
Listening.
your active listening.
Ah, the listening.
Yeah.
Yeah.
You got your grades back?
Yeah.
Yeah, okay. Happy or unhappy?
Wait, you're just
Not happy. Too hard?
No, it got much lower than I expected.
I think most people, this is what happens.
No, like a month ago, 2 months.
Wait, the bad science one?
Yeah.
Is
That was 2 months ago.
That was fun.
Continue. You got that now? Okay. We talked about this, so I don't need to continue talking about it. So again, well, I'll just be clear, maybe with an example. So here's an electron in orbit. Okay. So there's the proton. There's the electron. Now, if the electron falls, what happens to its potential energy? Does it become more negative or less negative? It falls. What do you think? More negative. Because maybe you know this in chemistry. Which is easier to free? The electron up here or the electron down here?
Up there.
Up there, yeah. So that means the guy here has more negative energy. Okay?
Yeah.
Yeah, you know this from chemistry, right? So, tell me what happens then. If the electron was here, but then all of a sudden it just falls to a lower level, what happened to its energy? So for its energy got bigger or smaller? No, smaller. Smaller in that it's more negative, you know. So like if this was -1 electron volt, then on this level it's -2 electron volt. It's more negative because it's more trapped. But energy can't just be destroyed or created. So what happens is, when this electron falls from this level to this level, then it releases a photon. And that photon will have the same energy as the difference here and here. So if we call this one PE1 and this one PE2, which do we say is bigger? PE1 is bigger, because PE2 is more negative. So PE1 should equal PE2 plus HF. This is the energy before and this is the energy after. In other words, HF will equal the change in potential energy. Now, when the electron falls, it releases a photon. If the electron is already here and you want it to go back up, then it needs to get a photon. Then it can move up a level. You get the idea? You don't need to write this down because we're going to have a look at an example. So we have an electron, and the electron is in orbit 4. So you know you have orbit 1, orbit 2, orbit 3, orbit 4. This is the energy in orbit 4. It then falls down to orbit 3, and a photon is released. What is the energy of the photon? Okay, how would I get that? So here it is in orbit 4. It falls to orbit 3 and releases a photon. What's the energy of this photon? Oh, I mean to say, how could we calculate how much it is?
Sorry, good question.
Here's the electron in orbit 4. it falls to orbit 3, and as it falls, it releases a photon. So a photon comes out. How could I calculate the energy of this photon? That's it. E4 minus E3. That's the answer. Because the energy it lost when it fell, that difference must equal the photon's energy that was released. Okay? So yeah, what is E4 minus E3?
0.3.
0.3? I don't think so. 0.
Oh, sorry.
That's 0.3. What is it? 0.66 electron volts. Okay, is that okay? Yeah? Do you need to write that down or? No. Oh, okay. Well, the next one I'd want you to write down. So, you have what's called the ground state. That's the first orbit. The energy is minus 13.6 electron volts. It receives a photon which causes it to jump to energy state 3. Let me draw that for you. So here's the nucleus. Here's the electron. It has an energy of minus 13.6 electron volts. Then a photon comes in and hits it. And this causes it to jump up to a higher orbit of energy minus 1.51 electron volts. Okay? And my question is, what is the frequency here of this light? Now let's try and think about this together. So, when it went from here to here, did it gain or lose energy? Gain. Where did it get this gain from? From the photon. Here. So that means the energy of the photon must equal the gain. Here and here. Well, what is the gain? The gain is minus 1.51 minus 13.6. What's that, please? 12.09? 15? 12.09? I think you typed something wrong there, Joe. So the last thing to do is just to convert this into joules by multiplying by E and then dividing by H. You have the answer. Now look, this is in the exam. This is why I say do the atoms question. Because these calculations are quite short. Okay. So can you give me the F here, please? What is it going to be for this F here? Two point nine two.
10 to the 50.
2.922 10 minus 53.
Huh?
Ah!
Type roll?
No. I believe your answer, Chow. 2.92 times 10 to the 15 hertz. Yeah. So if you go back here for a moment to this picture we had earlier, here. So the light comes in and makes the electron jump up. Where did the light go? It's gone. It was taken by the electron. That light is gone. So in this picture here, the light comes into the gas and it disappears because it makes the electron jump up. So this frequency here must be one of these black lines. Must be one of them, representing the missing colour. Yeah? Okay, good. Right. Where are we in that? Whoa. And I have a little video here. You can watch this later if you like. Yeah, and then I just have. Okay, so we got. I've still got a couple of things to do. Japers. Right. Right, what I'll do, there's a video here I want you to watch, because I just want to explain one thing, and then we can finish. Right. In physics, there's two main things you care about. You have things which are particles or waves. So particles look like this, and waves look like this. How can you tell if you have a particle or a wave? It's very simple. What you do is you take a double slit, and you have your material here, and you fire it through the double slit. If it's a particle, yeah, it will, some of them will go through this slit, some of them will go through this slit. So what will happen is you get detection here and here on the screen. Fair enough? So you fire it through the two slits, and then when you look at the screen, you get detection here and here, because there's two holes. Okay. Now, if you had a wave, I think you might remember this when we did our waves. If there's a wave that passes through, what image do you get here on the screen?
There will be smaller waves after the hole that I showed the image.
Yeah, so what image would we get here? You know this. Yeah, no, this diffracts, this is true. But my question is, what image do you get here? Say again, yeah? That's it, yeah. You get the dark and bright spots. You remember this? And what's this called? Fringe pattern. Do you remember this? Yes? Okay. So my question is, I have here electrons, and the electrons get fired out. What image will I get here? Will I get two detections or many detections? We think we should get two. Yeah? Why many? Say again? Well, we should get two, because what is an electron? Is it a particle or is it a wave? It's a particle. So particles should, when they hit the screen, some should go this way, some should go this way, and we should get two. However, very strange for the electron is that we don't get two, we get many patterns, which means the electron is behaving like it's a wave. But it's not a wave, it's a particle. This is very, very strange. Now it gets a little bit stranger too. So this is the last thing I just want to talk about. So here's electron gun. Fires the electrons. Now imagine you put a little machine here, and the only job this machine does is it tells you if the electron went left or if it went right. So here comes the electron, it's coming along, and it smashes here and goes left. So the machine goes left. And then the next one maybe smashes here and the machine says it went right. Okay? What picture would you get up here? Have I changed the experiment? No. What's the only thing that's different? This is being detected. So what if I told you that it now becomes this pattern? It does. Only two. Now, if you turn this machine off, so you don't know if the electron went left or right, this turns back to being a wave pattern. Meaning the electron knows it knows if you're trying to figure out if it's going in the left or the right slit. And this can even be seen at the last second. So you put a little detection machine here, and you want to see the electron moving in the space. So you say, oh, here comes the electron. You turn the machine on. Oh, it's turning left. And maybe here comes an electron. Oh, it's turning right. So you have a dot here and here. You turn this machine off, and then the electron goes back to behaving like a wave. That's fairly strange. How does the electron know that it's being observed? Right? It's very, very strange. Huh? Not quite that, but quite strange though. This gives us the kind of key thing which we'll talk about next time. So we said that light is a wave, but it moves like a particle. This means that particles, like electrons, can sometimes move like a wave. And how to make it move like a wave is kind of in an experiment like this. I think it's really, really strange because, just think about it. Here is the person here. Okay, the machine is off. The electron comes along here, but it behaves like a wave. So it's behaving like a wave. So it's just about to hit the screen and make a fringe pattern. But just before it hits the screen, you turn the machine on. And then all of a sudden, these waves turn back into electrons here. Very strange, right? But think about what that means. That means the wave almost went back in time and decided to behave like a particle and then continue forward because you turned the machine on. Yes? You understand why this is such a strange topic. So what we're going to have a look at next time is de Broglie's formula for calculating the wavelength, and then we have an example, and then we have an application of this, and then we're finished. When's our next class? Is it tomorrow? Oh, but I said I wanted to work on the coursework tomorrow. So, is our next class Wednesday then, or Friday? Friday. Okay, so we'll finish this on Friday, and then we'll start our revision. If you want to see a good video, you can go to YouTube and type in quantum double slit.